Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello. Yes, it's also my pleasure to welcome you to the opening of our second series. I think we have assembled also this time a very nice line of speakers that starts today and goes fortnightly until end of February next year. Our series complements the series that is more on climate. Our is more on general on sustainability and earth science. And so we really try to have a broad spectrum of topics that transcend climate, like ecosystems, also biodiversity, food security. And what I really like that we have a couple of contributions that really take the human factor also into account. And this will be also in particular the first speaker of the series, Hannah Druckenmiller, who will talk today about basically mapping humans, if you want, globally with machine learning and Earth observation. So it's really my pleasure to welcome Hannah here. She's actually a graduate from Berkeley and has recently been appointed as assistant professor at Caltech, assistant professor of economics, and she's really an environmental economist and combines it with data science. Her research aims to provide empirically based estimates of environmental benefits and economic costs associated with natural resource protection. And in this realm, she is really developing novel methodologies, integrating Earth observation with other data to learn more about the humans and the human imprint on Earth. So I'm really looking forward to listen to her talk together with you.
Hello, everyone. Thank you so much for joining, and thank you to Marcus and the organizers for inviting me to be part of this really exciting series. Today, I'm going to be presenting a project that's joint work with two of my co-authors at UC Berkeley, Luke Sherman and Saul Shang, as well as John Proctor at the University of British Columbia and Heriberto Tapia at the United Nations Development Program. The goal of this project is to produce global high-resolution estimates of the Human Development Index, or HDI. The HDI was developed to be a more comprehensive measure of human well-being than income alone. It also accounts for the population's health and level of education. And in developing these estimates, we're going to introduce a new method for downscaling coarse administrative data, such as data measured at the state or province level, that can be used more generally to track progress towards the Sustainable Development Goals. So I'll spend some time at the end of the presentation talking about that method and how you can engage with it. But first, I'll discuss our estimates of the HDI and how they can be used. So the big picture motivation for this project is that there is now a very large network of satellite sensors that deliver incredible amounts of information to Earth every day. And these data hold very strong potential to improve our understanding of global change and human development. And in particular, they offer strong promise to track progress towards sustainable development goals. This is really key because we know that data on these goals is scarce, especially in the places we need it most. Countries that are underdeveloped often have limited capacity to collect high quality data that can allow us to track progress towards these goals, and that can hinder our ability to direct resources towards where they're needed most. Over the last several decades, researchers around the world have been leveraging satellite data to improve our understanding of what's happening here on the ground. This started in the early 70s with the launch of Landsat, and originally the focus was really on understanding what the Earth's land cover looked like, where people lived, and so forth. The trick here is being able to translate the imagery that we get from satellites, which contains visible and light spectrums that we can't see, into information that we actually care about, such as maps of poverty or land cover or other sustainable development goals. But the shift in recent decades has really focused from understanding what's on the ground to being able to measure human well-being. And in particular, researchers in the last few years have leveraged satellite data to map things such as wealth, which can help us target aid and other policies that can help improve human well-being. Now, these estimates are not perfect, no model is, but they can still be very useful at helping us understand where people need resources most. A major constraint, however, is a lack of data on which to train these algorithms that translate the satellite imagery into indicators of things that we care about. So a lot of recent research has focused on using data from the DHS, which collects high-quality ground truth data on people's assets that can be then translated into a wealth index. However, these data are imperfect because they only measure a subset of the Earth, and they also have this feature that allows them to protect privacy, where DHS data have jittered coordinates. And so it's actually not possible to connect a DHS survey with the actual image of that location. Now, researchers have creative ways of getting around this, but limiting ourselves to the DHS really limits our ability of what we can do with satellite data. So it would be great if we could use other data sources, such as course administrative data from censuses, to actually train satellite algorithms. And that's what this project aims to do. And in particular, we are going to aim to produce global high-resolution maps of the Human Development Index using only provincial level data that was produced by researchers at the Global Data Lab. So let me talk for a second about what the HDI is. The HDI was produced to be a more comprehensive measure of human well-being than income alone. It also accounts for the population's health and level of education. And it does so using 4 basic indicators. So it measures health using your life expectancy at birth. It measures your level of knowledge using 2 indicators of schooling, expected years of schooling and mean years of schooling. And then it measures your standard of living using GNI per capita, or gross national income per capita. Those things all come together to produce one measure of human well-being, which is an index that measures between 0 and 1. Estimates of the HDI are produced every year by the United Nations Development Program. And so we get these nice country-level data sets that tell us which countries have relatively high HDI, such as the United States, countries in Europe and Australia, and which countries have relatively low HDI. You can see that purple there in sub-Saharan Africa and again in South Asia. These estimates are very useful for directing global resources, but they have a very coarse resolution, right? They're only produced at the national level, which limits our ability to use them in on-the-ground policy applications, such as targeting aid allocations or evaluating poverty alleviation programs. To partially address this, researchers at the Global Data Lab recently processed extensive household survey data to produce higher resolution estimates of HDI. So these researchers produced estimates at the first level administrative unit, more commonly known as a state or a province. I'm going to call this provincial for the rest of the talk, but you can have a state or a province in the back of your head. The goal of this paper is to further downscale these estimates, we're going to produce global estimates at the second level administrative unit. So you can think of this as a county or municipality. I'll call it a municipality for the rest of the talk. And we're also going to produce very high resolution gridded estimates of HDI. These are going to be on about a 10 by 10 kilometer grid. So again, our goal is to produce very high resolution estimates of the HDI. We're going to do this by combining satellite imagery, including both daytime and nighttime imagery, with coarse measures of the HDI, those ones that are at the first level administrative unit or the provincial level that were produced by the Global Data Lab. The goal is to produce HDI that's fine enough resolution to actually use in policy applications, such as targeting aid, and to also develop a generalizable method for training satellite data and machine learning algorithms on coarse administrative data, such as provincial level data. And it's our hope that this algorithm will open the door to using much more data in the training of machine learning algorithms that can track progress towards the Sustainable Development Goals. Okay, so the big challenge here is that we don't actually have data on HDI at the level at which we want to produce estimates. So we want to produce very high resolution estimates of HDI across the globe, but we only have coarse provincial level data. Now, if we had data at the level of which we want to produce estimates, say at the level of a satellite image, then our task would be to learn the relationship between satellite imagery and our outcome of interest, HDI. So to come up with a functional form for that function f here on the slide. The challenge is that we don't actually have data at the level at which we want to produce these estimates. We're going to address this challenge by specifying that function f that translates imagery into HDI as linear in a set of image features. What that allows us to do is to then aggregate up those image features to the provincial level where we do have measures of HDI and learn that linear relationship in the data that we do have. So in particular, we're going to be coming up with an estimate for beta here, which is going to translate image features into HDI. The nice thing about a linear function is that it's scale invariant, so that we're able to learn an estimate for that parameter beta in the coarse provincial data, and then we can actually apply it to predict HDI at other spatial scales. And in particular here, we're going to focus on predicting HDI at the municipality scale. So the magic here is coming up with a set of image features that allow us to estimate such a linear function and still have skillful power at predicting HDI. So our approach to doing that linearization is going to lean on an algorithm called mosaics, which was developed by researchers at UC Berkeley a couple years ago and is outlined in this really nice paper by Rolf et al. I'll give you a brief overview here, and then I'll revisit this algorithm at the end of the talk and talk about how you could engage with it in your own work. So the basic idea behind mosaics is that we want to come up with a set of image features that is sufficiently rich that it contains structured information on the very unstructured information that we see in imagery. How we're going to achieve this is that mosaics takes a sample of random patches from your full sample of satellite imagery. So you're going to grab these little squares from your images. Those are going to be your patches. For each patch, you're going to convolve that patch over each image in your sample. And that's going to lead to an activation map for each patch and each image. We're going to take some sort of summary statistic over that activation map, such as a mean or a sum, which is going to translate that map into just one number for each feature that describes how like the patch each image is. So let me give you a little bit more intuition for this, but the basic idea here is that we're translating each image into a vector of features that we can then specify a linear function with. Okay, so what are these features? So imagine that we have an image here that contains information in it. We can visibly see that on the top left of the image, there's a forest, there's a road running down the middle, and there's a body of water on the bottom right. We're going to randomly sample some patches from this image. Patches are just little pieces of the image. In this case, they're going to be a 3 by 3 square. The first patch was sampled from the forest part of the image. It looks green. And when we pass it over the image, it's going to light up or activate in the areas of the image that have trees. The second patch was drawn from the area that has a road. When we pass it over the image, it's going to light up in areas that have built infrastructure or roads. The third patch was drawn from the body of water, and it's going to light up when we pass it over bodies of water. If we collect enough of these patches, then we'll have sufficiently rich patches that we're actually able to describe many diverse characteristics of the image intensity and its texture. And so, in fact, we're going to take about 4,000 patches from all of the imagery in our sample. And by applying this mosaics algorithm, we're going to collapse each image into a set of characteristics, or this vector of image features that you can see here indicated by X. That's going to contain one number for each patch that basically maps to how like that patch each image is. This is going to allow us to downscale the administrative data on HDI into higher resolution estimates of HDI using the satellite imagery. Now, using imagery for downscaling is not a new concept. This has been applied for decades. In particular, researchers have used satellite data on built-up area, for example, to downscale administrative population counts by assigning people to where buildings are. Researchers have used data on nightlights to downscale economic measures to where the nightlights are. And recently, researchers have been using greenness, or NDVI, to downscale agricultural yields data. So our approach using mosaics is going to follow similar intuition, which is that we can downscale these administrative data using machine learning and satellite imagery. But the benefit of using mosaics is that it's going to allow for much more complex multidimensional relationships between the image and the outcome. And the really nice thing here is that the researcher doesn't actually need to know that relationship between the image and the outcome in advance. Mosaics is going to take care of that for us. So this is really useful in our setting where we don't necessarily know the characteristics of each image that map towards HDI. It's not as simple as, say, assigning population counts to where buildings are. All right, so there's a lot going on this page, but let me briefly walk you through it to understand what we're actually doing here. So we have data on HDI at the provincial level. Here I've taken out one province in Ethiopia, and I'm showing you the corresponding satellite imagery on the top of the image. Our goal is to take that imagery and to translate it into a vector of features that we can then learn a linear relationship between those features and HDI. So we're going to take this provincial level satellite data, and we're going to tile it up into little pieces, which you can see here on the bottom left, examples of tiles that correspond to this province. And you can see that there's many different things happening in this province. There's agricultural area, there's barren land, there's built up area. For each of these tiles, we're going to apply the mosaics algorithm. So we're going to pass those patches over the image, light up activation maps, and that's going to tell us for each patch how like the patch each image is. You can see an example of 3 different features here in column D. We're starting with feature 1, feature 2, and then you can imagine thousands of more features all the way down to feature K. Those features are going to produce a map for each feature that shows how like the province is to the patch that we passed over it. We're going to then take those very high resolution maps, and we're going to aggregate each feature up to the provincial level, like you can see here in column E. The reason that we have to do that aggregation, again, is that we only have data on HDI at the provincial level. So once we have that province level data on features, we can learn the relationship between HDI and image features. And then we can take that relationship that we learned, because it's linear, and apply it at a different spatial scale. So in particular, we're going to then apply it at the municipality scale. That requires us to take the image features from column D and aggregate them to a different spatial scale in column F. This is a higher resolution scale. And then we can take our algorithm that we learned in the provincial data and apply it to the municipality data. So let me just repeat that process in math. So we are going to learn the relationship between HDI, daytime imagery, and nighttime imagery at the provincial level. we're going to do this in a way that allows us to use a linear function in the imagery. Because that function is linear, we can apply those betas that we learn to predict municipality level HDI using imagery at the municipality level and the same betas that we learned in the provincial level model. Okay. After we make these estimates, we're going to try and convince you that they contain useful information in them. We're going to do that in two ways. The first way we're going to do it is the traditional way of evaluating the performance of a machine learning model, which is to show you the performance of our model at predicting HDI in a held out test set. We can do this at the provincial level because we can observe measures of HDI for each province in the globe. However, what we really want to know is how well we're doing at downscaling HDI below the provincial level. And here it's hard to directly evaluate our performance because the whole point is that we don't have measures of HDI below the provincial level. That's what we're trying to produce here. So we're going to perform 3 different exercises that we hope together will convince you that these estimates do in fact contain useful information. The first exercise is going to use an analogous exercise using nightlight data. And the reason that we're going to focus on nightlights is twofold. First, nightlights are highly correlated with economic activity and human well-being. And second, we can observe ground truth. We have high resolution data on nightlights everywhere. So what we're going to do is we're going to repeat our exercise that we do with HDI for nightlights. We're going to only allow ourselves to see provincial level nightlights. We're going to train our model. We're going to predict at higher spatial resolution. And then we're going to unhide the high resolution nightlights data from ourselves in order to evaluate performance at the level at which we make predictions. The second exercise we'll do takes advantages of DHS data, which allow us to measure the International Wealth Index, or the IWI, at the village or cluster level. Here, we're going to, again, learn the relationship between IWI and satellite imagery at the provincial level, hiding the higher resolution data from ourselves. We're going to make predictions at the DHS cluster level. Then we'll unhide those data from ourselves and evaluate performance on the high resolution data. We use the International Wealth Index, or IWI, here because it's one component of the HDI. So those 2 indicators should also be highly correlated. And then third, the most direct test of our downscaling is possible in Mexico, because the same researchers from the Global Data Lab who produced the provincial level estimates globally of HDI have also produced municipality level estimates of HDI in Mexico by processing census data there. And so in Mexico alone, we're able to compare our municipality level HDI estimates that were produced from satellite imagery with estimates that were actually produced from census data. Okay, so let me start with the provincial level performance, which is, again, the classical way of measuring model performance in machine learning, where we are evaluating performance on a held out test set. And in particular, we're holding out entire countries so we see how well our model performs out of sample. So here on the left of the slide, you're seeing what we're calling the full variation performance. So this is our predictions of HDI on the x-axis against observations of HDI from the Global Data Lab on the y-axis. And you can see that in the full global sample, we're achieving quite high performance. So we use 2 measures of performance, R squared and rho squared. R squared is telling us how much of the variation we can explain with our algorithm, which is about 95%. Rho squared is telling us whether we're getting the ordering in HDI across provinces, right? And that's a pretty similar metric of 0.95. Importantly here, we are actually mean anchoring our estimates. And what I mean by that is we are using the information on country level HDI that the UNDP produces to anchor our estimates to those known country means. And the reason that we do this is that that's really useful information. We don't want to toss it out. We actually want to use it in producing our downscaled estimates. On the right here, I'm showing you a second measure of performance, which is our performance within each country. So on the left, we were showing you the performance within the full global sample of getting the provincial HDI measure right. On the right, we're showing you how well we do at getting HDI right when we limit ourselves to looking at within country variation. And this is a much harder task because on the left-hand side, you see a lot of you see a lot of variation between provinces in different countries. On the right-hand side, we see much less variation in the data, and so it's a harder task to explain that variation. The difficulty of that task is kind of illustrated by highlighting provinces in two countries. So in yellow, I'm highlighting provinces in France, and in red, I'm highlighting provinces in Ethiopia. So you can see that if we are looking at the full global sample, it's very easy for the model to pick apart which provinces are in relatively well-off France, as opposed to relatively less off Ethiopia. But when we're only looking at variation within country, it's more difficult for the model to disentangle which provinces in France are better off than other provinces in France. Still, however, we're able to predict about 45% of the variation and differences between HDI among provinces within country. So the algorithm is providing useful information that can be used for downscaling. Another important thing to note here, just methodologically, is that we're training on the anomaly of within country HDI. So what I mean by anomaly is we're taking the mean HDI within each country and we're subtracting it from the provincial HDI. And then we're training our model to predict those deviations from the mean rather than just the level of HDI. What this allows us to do is to optimize the model to predict within country variation as opposed to across country variation. So it allows for better downscaling. I saw an image in the chat about what imagery we're using. Thank you for bringing that up. We are using imagery from Planet for the daytime imagery. So that's about 4-meter resolution imagery for the entire globe. And then we're using the nighttime imagery from Virus, which we have multiple years of data and we're collapsing it into one global cross-section. Okay. So a few other notes on the model's predictive performance. We are able to get a signal for each of the components of HDI, so income, schooling, and life expectancy. We're not only predicting income or only predicting life expectancy. However, I should note that all three of these indicators are highly correlated, and we do better on income than on health. Importantly, the performance of the model is highest in the countries with the lowest HDI, which is arguably where we need these prediction most. This is in places where we have less capacity to collect on-the-ground data. And part of the reason for that higher performance is that there's just more variation in HDI within these countries. And so it's easier to predict within country differences in HDI. And then a third note on performance is that combining daytime and nighttime imagery does perform better than either imagery source alone. So it's important to include both sources of information when you're tracking human well-being. Okay, next I'm going to turn to our exercise where we evaluate our performance at downscaling. And just as a reminder, our first exercise performs the analogous exercise that we do on HDI on nightlights data. And the idea here is that we can observe nightlights across the entire globe at high resolution. So we have a measure of ground truth on which we can evaluate the performance of our higher resolution estimates. So what we're going to do is we're going to take those global nightlight estimates, we're going to aggregate them up to the provincial level to mimic the data that we can see in our HDI case. We're going to train our model only on those provincial level observations, and then we're going to use them to predict municipality level nightlights. The predictions are shown here in panel C. We're going to take those predictions and we're going to compare them against the true nightlight measures, which we then aggregate to the municipality level from the raw data. And that allows us to calculate our performance at predicting municipal level nightlight measures. This exercise shows that we can explain about 78% of the variation in municipality level HDI, or municipality level nightlights, using a model that was trained at the provincial level. So here's that same information in scatter plot form. On the left here, you can see the full sample performance. That's the R-squared of 0.78. And again, we evaluate performance both within country in the middle panel and then within province in the right-hand side panel. And so that right-hand side panel is really telling us how well we're doing at downscaling nightlights below the provincial level. And here we're able to explain about 60% of the variation of within province variation in night lights. So this is giving us confidence that we can actually train a model at coarse spatial resolution using this mosaics algorithm, and then predict at higher spatial resolution and still create skillful predictions of what's happening within those provinces on which we trained the model. The next thing we do is we conduct a similar exercise using the International Wealth Index, or IWI, from the DHS. So this is a measure that is available at the cluster level. A cluster usually relates to a village. And so we're able to, again, train a model on the provincial level data after aggregating it up, then apply that model to predict village level IWI and see how well we're doing when we use a model trained at coarser resolution than which we make predictions. You can see the same three graphs here. On the left-hand side, it's our full variation performance, predicting IWI at the cluster level. We have an R-squared of about 0.68. That's doing pretty well. If you move all the way to the right, it's a much harder task to predict variation in IWI within each province because a lot of the variation is across provinces, but still we're able to explain about 40% of the variation in IWI within province. And so finally, we'll show you our last test of downscaling, which is comparing our satellite-produced estimates of HDI at the municipal level to municipality level estimates of HDI in Mexico that were produced by processing census data. So this is the most direct test of our performance. It would be great if we could do it everywhere, but unfortunately we can only do this test in Mexico because that's the only country for which we have municipality level HDI measures. So you'll see again here that we are able to predict some variation in within country and within province HDI using this downscaling method. Now, I want to note here that these R-squareds aren't the shiny 0.9 that you might see in models that produce estimates of land cover. Socioeconomic variables are harder to remotely sense, and this within province measure is actually quite unstandard in the literature. But we think it's a measure of the added information that we're able to provide. Since we already know provincial level HDI, we're really interested in producing measures of HDI that add information beyond that. And so anything that's R-squared above 0 is adding information here. Another thing you'll note from this exercise is that there is a compression in the HDI estimates that we're able to produce using the satellite imagery. So the variance of them is kind of squashed compared to the observed values. This is quite a common characteristic of machine learning models, is that they tend to compress the variance because it's hard to predict outliers. So that's just something to note when you're viewing and using these data. So hopefully now we've convinced you that this method is able to actually add information on HDI below the provincial level. And so what we do is we then deploy this algorithm to predict HDI at the municipal level. We do this for every year between 2012 and 2021. And on a higher spatial resolution grid, this is a 0.1 degree by 0.1 degree grid, which corresponds to about 10 by 10 kilometers. So here you can see these nice maps of HDI at the global level. I'm going to zoom in to a couple of case studies to show you what's happening. So on the left-hand side here, you can see the municipality level predictions, and on the right-hand side, you can see the grid level predictions. And we're able to zoom into areas and see that you can actually see cities lighting up. You can see roadways, and especially the intersections of roadways lighting up. You can see higher HDI on coastlines and rivers than in inland areas. All of these patterns match our intuition and convince us that these data are actually able to predict local level variation in HDI that could be used for policy applications like targeting aid. So we make these data available for free on mosaics.org. If you want to take a look at them, there's a nice interactive database where you can download the data there. And I'm going to show you two use cases here of how these data could improve our understanding of the distribution of human well-being that will hopefully spark ideas for further use. So the first use case is understanding the global distribution of HDI. And in particular, we're interested in understanding the distribution of HDI within countries, since that's the added information from these new estimates. So this is a Sankey diagram for those of you who haven't seen one of these before, and it essentially shows flows between groups. So on the left-hand side, you can imagine that we previously assigned everyone in each country to an HDI quintile based on the state level data. So everyone in this pink rectangle at the top would be assigned to the lowest HDI quintile using the state level data. Everyone in this yellow square at the bottom would be assigned to the highest HDI quintile using the state level data. Then we're going to reassign everyone to a new HDI quintile using the municipality level data that we produce here. And so everyone, those estimates are shown on the right-hand side. So everyone in this pink box on the right side was assigned to the bottom HDI quintile using the municipality level data. And what you'll see if you follow the flow lines is that about half of people that were originally assigned to the lowest HDI quintile are assigned to the same quintile using the more spatially granular data. But about half of people move to a different HDI quintile. And in fact, people are moving all the way to the top HDI quintile. And you see the same thing if you're looking at movement from the top HDI quintile from using the state level data here at the bottom. So we're actually reassigning people to different quintiles of the distribution using this more granular data. Why is that useful? Let me just show you a simulated exercise in Mexico that I hope will impress why having a more granular estimates of HDI can be useful for actual policy applications. So imagine that we have a policy, say it's aid, that we want to target towards the 10% of individuals with the lowest levels of HDI. Now, because it's difficult to measure HDI at the individual level, the administrator previously only had measures of HDI at the state level. And so before knowing municipality level HDI, they had to assign eligibility for this program at the state level only, or the provincial level only. You can see in panel A what would happen if the administrator assigned aid in that fashion, where it would be targeted towards these three provinces shown in red here. Now imagine that the administrator can actually see HDI at higher spatial resolution. So we're now giving them these municipality level maps. And so they again assign the same 10% of the population. They again want to assign aid to the lowest 10% of HDI population, but now the program is targeted towards the municipalities highlighted in red in the bottom panel here. So we actually have a much different distribution of aid than we were seeing using the state level data. And in fact, in Mexico, we estimate that this improves the accuracy of targeting by about 25%. So the idea here is that more granular estimates of HDI can be used to improve aid targeting or to do program evaluation for poverty alleviation programs where we really need to observe local level changes in HDI. Okay, if anybody wants to use the HDI estimates we produce, we provide them on mosaics.org. So you can simply go to the website and download these data. In addition to providing the HDI estimates that we produce, we also provide the image features that we produce aggregated to administrative units, such as countries, municipalities, and provinces. And the really nice thing about using these image features is that they're much easier to engage with than the raw satellite data on their own. And I'll talk through that in a minute in more detail. But one way of seeing that is just by looking at the size of the data sets. If you were to use the raw imagery that we used in this analysis, so that's 4-meter resolution imagery for the entire globe, that would be about 30 terabytes of data. We translate that into those image features that you can use in a linear regression to estimate your outcome of interest. Those global features at a 1 by 1 kilometer resolution are only 3 terabytes. So they collapse the size of the data by an order of magnitude. If we then further aggregate those image features to administrative units like municipalities or provinces so that you can connect them with census data, the size of the data becomes much more manageable, less than 3 gigabytes per file. So this is something that you can actually engage with on your laptop computer. Okay, let me backtrack for a minute and talk a bit more about the mosaics algorithm. Here we use it for downscaling, but it can actually be used more generally to directly predict outcomes of interest, as long as you have any ground truth labels. So the idea behind the mosaics algorithm, which was again produced by a team of researchers at Berkeley a couple of years ago, is that it makes satellite imagery and machine learning accessible to non-experts and people without access to high computing power. And the way it does this is that it takes the very unstructured and messy data that's contained in an image, and it collapses it into a vector of image features, these X's here, that are sufficiently rich to actually be able to describe what's happening in the image. The nice thing about these images is these image features is that they're task agnostic. And what I mean by that is that they do very well at predicting many different on-the-ground outcomes. So let me just illustrate that through a simple example here. Say I'm a user who's interested in producing maps of forest cover in South America. And say I have some ground level estimates of forest cover from ground surveys. So those are my Ys, my ground truth labels. I can go to mosaics.org, I can download these image features, and I can spatially match them with my labels of forest cover at those ground truth sites. And then I can learn a simple linear regression. In this paper, we use a ridge regression, but you can imagine using other models that translates those image features into a prediction of forest cover. I can go out and I can deploy that algorithm to fill in the entire map of forest cover in South America. Now imagine that I'm a different user. I'm an administrator in India who has some village level counts of population. I can go to mosaics.org. I can download the same set of image features, learn a relationship between those image features and my village level population counts, and then deploy that algorithm to predict populations in villages for which I don't have ground truth data. So the really nice thing again here is that this is something that anybody who knows how to run a linear regression can engage with. We've done the hard work of downloading and processing all that satellite data into a format that's easy to engage with, these vectors of image features. And so it's up to you to then do the last step of connecting them with your outcome of interest and learning that model. Okay, the original paper that introduces mosaics shows you that mosaics has high performance across a wide variety of tasks. So in this paper, they looked at 7 different outcomes ranging from forest cover, elevation, population density, nighttime lights, income, road length, and housing price. And they showed that mosaics is actually able to produce skillful predictions across each of these outcomes. This figure here is from the United States. They also did this globally. So it's not just limited to performance in higher income countries. And if you're wondering how mosaics compares to state-of-the-art machine learning algorithms, here's a nice figure from the paper where they compare the performance of mosaics with that of a deep convolutional neural network. So the performance of mosaics here is shown by the darker bars. The performance of the deep CNN is shown by the middle shaded bars. And then there's also a pre-trained CNN shown by the light bars for comparison. And each color corresponds to a different outcome, which you can see indicated at the bottom of the graph here. And so what you'll see is that mosaics often performs competitively with that convolutional neural network. Here they use a ResNet 18, which is kind of a workhorse CNN. And the performance isn't identical, but it's, very competitive with the CNN. And this is despite the fact that mosaics, you can estimate the model using a linear regression. And these models take about 3 minutes to run as compared to multiple days of a deep CNN. Okay, so if you're interested in engaging with mosaics, we've created an API that makes these image features available for every 1 by 1 kilometer grid cell across the globe. And you can upload a polygon or a set of lat lons and download the image features for those locations. In order to make this even easier to engage with, we've also put together some tutorials. So there's a video that you can go to that walks you through how to download and use the data. And there's also Python notebooks that have example use cases. So you can walk through those, and then you can even try and go in and substitute out the outcomes that we're predicting with outcomes that you might care about if you have your own ground truth data. Okay, so I'm going to wrap up now. And I'm really looking forward to questions at the end of the talk. So in this paper, we use mosaics to produce global high-resolution estimates of HDI. And more generally, we introduce a method for learning satellite imagery and machine learning models on coarse administrative data, and then using those algorithms to predict outcomes of interest at higher spatial resolution. We really like this approach because we think that mosaics makes remote sensing accessible to many more users. It doesn't require expertise in deep learning. It only requires knowing how to run a linear regression and a laptop. Still, it achieves performance that's competitive with deep learning models. And one really nice thing about mosaics is because it's so fast to run, you can learn these global models in a matter of minutes. It allows us to actually characterize uncertainty in a way that's less common with these kind of big workhorse models that are harder to train and more computationally intensive. Still, mosaics is not a silver bullet. It doesn't replace the need for detailed ground surveys. We need those data to obtain really high quality information on what's happening on the ground and to train our machine learning algorithms. And it doesn't replace the need for more specialized model development to get those extra few percentage points of performance. Lastly, I want to be very clear that mosaics doesn't go over time yet. So we're producing kind of cross-sectional snapshots of what's happening on the ground. We haven't yet perfected predicting changes over time, although that's something that our team is actively working on. So I'm going to end there. Thanks again to the organizers for having me. It's been really fun, and I'm looking forward to continuing the conversation through the question and answer.
Yes, thanks a lot for this very, very nice and clear talk, I think. So how we will do it now is we do have some questions in the chat that we can discuss. You can answer if there are. I would also have some. Let's see if I'm allowed, or if I can allow myself to ask 1 or 2 questions. But we start with a question from the chat. There's another one from Luisa Lucchese, who is asking about the advantages of the linear model. I think you addressed it, but maybe you want to repeat it.
Sure. So here we use a linear model because it allows us to train the model at a different spatial scale than we're predicting, then we're producing our estimates. And that's because that linear parameter beta is scale invariant. You could also take mosaics features and plug them into a nonlinear model, like a random forest. But here we focus on that linear model so that we can get that scale invariant model. I'll just note that even though the model is linear, the image features contain very rich nonlinear information about what's going on in the image. So it's kind of an oversimplification to think of it as a simple linear model. It's linear in this basis function that's actually highly nonlinear.
Yes, thanks. Thanks for the explanation. The next one is by Patty Brook, who thanks for this nice presentation. And the question is here, if you are able to, if this and how this approach would work in places of high deprivation, for example, where night lights are actually uncommon and population density is low. So might it be possible to use downscaling in a pre-specified way, for example, for the contribution of refugees versus host nationals living in administrative areas using socioeconomic microdata to kind of steer the process? There's a link mentioned that I don't know, but maybe you know it. You can also see the chat.
Sure. So in this In this project, we combine daytime and nighttime imagery, like I mentioned. And one really nice thing about that is that it really boosts model performance in areas that have low night lights. So night lights are great for predicting economic activity, but if a place isn't electrified, then we have no variation in night lights there. So by adding that daytime imagery, we're actually able to do much better in places that have low HDI. That doesn't fully address the question. There's also the question about areas with low population density. The model is learning from areas, even if there's no people there, because wealthy fields and forests in wealthy areas tend to look different than fields and forests in areas with lower HDI. But it is harder in places where there's less variation in HDI on the ground. And then the last thing about local level predictions. One thing that I didn't mention about these image features in the linear model that actually turns out to be quite useful, and we don't do it in this project, but you could in principle do it, is that because the image features are then aggregated to the level of an administrative unit, you could tack on many other predictors from administrative data to predict your outcome of interest. So you are not just limited to using the satellite imagery. It's seamless to actually integrate other data sources into these predictions. And so that can help with refining local level estimates and achieving higher performance.
Okay, thanks. Before moving to the next question, maybe actually I add one that was quite related to this question of model performance in different areas. So you mentioned basically the good performance in low income countries, let's say, and you mentioned that partly this is explained by that there's just more variability, so you get a higher R squared. But did you check that? I mean, you could check that by, for example, not comparing on the R square, but maybe something like an RMSE, although of course HDI is not a super quantitative variable, but comparing a variable with a metric that is not depending on the let's say variability, something like that. So is it better for that as well?
So we also use rho squared, which tells you how well you're doing at getting the ordering right. But the variation in the HDI doesn't only increase our performance because of the metric. It's really because there's more for the model to pick up on. Remember that we're training on the deviations between the country mean and the provincial level. So if all of the provincial levels are packed together close to the mean, there's very little variation for the model to actually learn on. In places where there's higher levels of variation, the model can actually more easily pick up those differences. And so part of it may be due to the measure we use, but I think most of it is actually due to the underlying variation in the measure. Is just there's more variation for the model to learn in those low-income countries.
But you didn't look at a kind of an absolute deviation or something. I mean, that would basically prove
No,
it.
but that's a good idea. The paper is still in review, so we have the chance to add additional measures.
So my next question is by Kali Tabor. Thanks for the outstanding talk. Why is the downscaling of HDR only from 2012 to 2021? Since the global data lab is available since 1900, but probably not the remote sensing data.
So that's because
the
the night lights data that we use is only available from 2012 to 2001. There is a different source of night lights data that's available going back further in time, but it's not measured using the same sensor. And so we just stuck to the one that we learned on. In principle, you could learn a model on the different source of night lights data and apply it to predict HDI further back in time. I do want to say, just as a disclaimer on the overtime estimates, that they do a good job of showing you the spatial distribution of HDI in each year, and they're anchored to those provincial means in each year, so they're reflective of variation within that year, but they shouldn't be used to compare changes in HDI over time because the model wasn't produced for change detection. And it actually doesn't do a great job of predicting those changes.
Yes, so the answer the next question by Luisa Luqueza, as the data is available from 2012 to 2021, do you plan continuous releasing for 2022 and 3 and so on? Yeah.
We do. So the nice thing about the model is that it only needs to be trained once, and then you can predict at very low cost. So we plan to continue updating the estimates as new global data lab estimates come out.
Okay. There can be more questions in the chat, but I had also one other one. So if I understood the mosaics approach correctly, the features basically that I extracted, they do not depend on the spatial arrangement of the features that are in the figure in the original image, except for the very local one where you use the kind of your patch. Is that correct?
Yeah, so it depends on the patch size. If you're using a very small patch, like a 3x3 patch that I showed in the example, then you're getting very local level texture. In this paper, we actually choose two different patch sizes, one which is smaller and one which is larger, to explain local level variation and more broad variation in the image. And we find that that performs better than using a single patch size alone. Yeah.
Yeah, thanks. Yeah. So, no, okay, there are no further questions on the video more. Okay. Then maybe I have one last that I really also had. So I mean, it's very nice, and you mentioned basically this scale independence, so you can basically go across the different levels. I was just wondering, there must be somehow from the information content still a sweet spot. I mean, or at least, for example, you had only 3 continents or something, and you cannot train on 3 points. So is that, do you have a feeling for that? I mean, at which level, maybe for another approach, one would only have country level data or something? Is that enough or not? And so on.
Yeah, it's a great question. So we actually did at first try and train the model using only the country level data just to see when you hit that wall. I don't remember quite off the top of my head, but I think our full variation performance there was an R-squared of about 0.7 compared to the 0.96 when you use the provincial level data. And then downscaling becomes harder. It's harder to explain within country variation. So in our case, we had the provincial level data is about 2,000, a sample of 2,000 training points. The country level data, I think, was a couple hundred. So you can still train the model on country level data. I wouldn't go below a few hundred training points. In the Rolf et al. Paper that I mentioned that introduces mosaics, they actually do a really nice exercise where they show performance across those 7 tasks as a function of your number of training points. And you can see like where it really drops off as you go low in the training points. And so that can be a nice resource if you have an outcome and you want to look at a similar outcome in their setting, whether it's forest cover or income, and see what your training point target should be.
Thanks. Yeah, very nice. Good. I think then it's again my pleasure to thank you a lot for this really brilliant talk and insights that you shared with us. I think now there's in principle the chance to connect a bit in the neural network that can be accessed in the website where people are also registered. Maybe there is some interest in networking on the topic and asking some more detailed questions or exchanging links and so on. That's an opportunity at least. And then I'm looking forward to the next talk, actually, also, which will be in 2 weeks by Dria Martini from the World Food Program, and she will talk about practical applications actually of machine learning for predicting famine and future hunger on a seasonal timescale. Thanks, everyone. Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.